Hi, everybody. This is Aaron Schwartz, and I'm calling this video Mesmerizing Means, but it's actually an introduction to box plots and statistics in the Algebra 1 curriculum. This is not going to be exhaustive of everything that students need to study, but it is going to be an introduction. And we are going to take a look at this very differently than we have previous videos. I'm going to be using an interactive Desmos graph that I've created. The link to this graph will be available underneath the video in the classroom. So let's take a look. How would we want students to start exploring statistics? Well, one of the most fundamental questions is what is the center? And it's not just what is the center, but where is the center and why are there multiple centers when we look at data? We actually look at a similar question when we're talking about triangles in the geometry curriculum. Why are there multiple centers? What does each center communicate to us? So let's take a look at it in terms of a univariate data set. We have a pretty simple univariate data set, 1 and 7. We only have data along one dimension, but we have these two data points. Engaging with students, one of the first questions we would ask is, where's the center? Now, students are going to only have one answer to that, and it's going to be pretty obvious, but we want to start with that very obvious question and then dive into some more complicated questions. So the center is something we would actually call, in this case, the mid-range. It's 4. 4 is evenly spaced from 1 and 7. Of course, we don't normally deal with data sets that are just two numbers. So a mid-range is not very useful and something we don't really discuss much when we're talking about statistics. The mid-range is just the middle of the range from the highest to lowest, but we don't normally have a data set so simple, so we don't normally care about the mid-range. So let's go ahead and add some middle points in there. Once I add these points, 2, 5, 5.5, 6, 6.5, now we have an issue because 4 really doesn't look like the middle anymore. There's some reasons why I might say that that is the middle between 1 and 7, but it's not really the middle of this data set. So one of the next questions I would want to ask students is where they think the middle is and whether or not they think there could be more than one middle. One student might actually clue in on something that we call the median, which is the middle data point. So if I click here to add my median, what I can see is that the median is dividing the data set into two equal halves. I've got 3 data points to the right and 3 data points to the left. Now, this is another type of middle, but again, it doesn't look so good because while it's the middle data point, it doesn't take into account that the data points on the right are really close together, and the data points on the left are really far apart. So I might ask students, is this really the only center we can define? Are there other centers? And some students may guesstimate a center somewhere between the 4 and say this point of 5, or at least somewhere between the 4 and the 5.5. They may actually say the 5 is a center. And then we need to ask them, what are you really defining the center of? What difference does it make if we have a third center? And this is where we want to get into some analogies. And this next analogy is not perfect. It is not uh, totally physically representative, but it's an idea to conceptualize it. And that idea is the idea of weights. So if we had equal weights at each of these points along a scale, where would we need to put the tipping point? How would we do that? What is that? Well, in physics, it's a weighted mean. It's actually something that comes up in statistics too. And it's the idea of balancing out the distance as well as what the weights are. Now, an arithmetic mean is not exactly this, but it does give us a context to understand the idea of balancing out both the distance and the values of the points. And so our mean is kind of like that. It's balancing out both the distance of things as well as taking into account the values of the numbers. Now this does some interesting things for us, and I'm going to turn off the mid-range for now. One of the things we can notice is that when the data points are really clustered together on the right side, but really spread apart on the left side, the mean was less than the median. So what if we reverse that? What if we clustered the points together really closely on the left side and then had the points on the right side really spread apart? So let's go ahead and move some points together. Here we have a lot of points clustered together on the left side and spread apart on the right side. And what's happened? Now our mean is greater than our median. So this is very interesting because if we know the median and the mean for a data set, we probably know where the concentration of the data is. This introduces the idea of skew very nicely. Because I can see that the data points are clustered together on the left, but they are spread apart or skewed on the right, I can now start to put together that if my mean is greater than my median, there's a very good chance that my data is concentrated on the left and skewed to the right. And the reverse is true. When I had a data set that was concentrated on the right and skewed on the left, my data was left skewed. So if my mean is less than my median, it's not certain, but there's a good chance that there's a left skew. I would need to know more to be certain, but I can guess that it's left skewed. If the two were perfectly equal, there's a good chance the data set is a normal distribution. So now let's start adding in a few things. I'm going to turn off the mean, and I'm going to focus on getting back to a box plot. Now with a box plot, what I'm really doing is dividing my data up into segments, or quartiles. I'm putting a quarter of the data into each segment. So that means I need to find the midpoint of the upper half and the midpoint of the lower half. So my midpoints are just going to be in the middle. So I'm going to divide it from between this 1, 2, and 5, and I need to find the midpoint of 1, 2, and 5, which will just be 2. Same thing with the 6, 6.5, and 7. And so I have my quartiles. Now from here, it's a very easy step to draw my box plot. My box plot's done. All I'm doing is showing a line to represent the lowest quartile of the data and the upper quartile, and boxes to represent the middle 50%. This offers us a very interesting conversation point. We had previously described this data as left skewed. And when we look at the box plot, we can see that the left side of the data is much larger than the right side of the data, which supports our left skew. That left side is spread apart. The right side is concentrated together. In fact, I can also do that same exploration that I did with the mean and the median right here to see how things change. If I want to go back to a right skew, I can just dynamically drag the dots. And now that they're concentrated on the left side, I can see that right skew. One of the other things that we need to keep in mind is that box plots don't really tell us all the information, especially when we're first starting to explore them. For example, when we first start exploring them, we don't necessarily talk about outliers right away. Now, most students will understand that an outlier is something that looks very distinct and different from the data. So let's build the data set so that we have distinct and clear outliers. What I'm going to do is I'm going to concentrate the data in the center. I'm also going to take this value of 7 and drag it further to the right to make it clear and distinct and different. So we now have this data set where there's data concentrated in the center and the extremes are way outside. So is this an appropriate measure? Well, now what we're going to do is we're going to trim our box plot to make sure that we can distinguish what exactly an outlier is versus what isn't. So we have this handy measure called the interquartile range. It's just the range of the middle 50% from the median, from the lower quartile to the upper quartile. And what we do is you take 1.5 times that amount. Now that has to do with how the bell curve is set up. But for now, we're just going to say it's 1.5 times the interquartile range. And we're going to both add it to the median and subtract it. And so we're going to look at something like this. Right here, we have 2 points. This represents the median minus 1.5 times that interquartile range. And this point represents the median plus that 1.5 times the interquartile range. Anything beyond or outside of those points is an outlier. And I'm going to put in some shading to help visualize it. So anything beyond those barriers represents an outlier. So this box plot is no longer appropriate. In fact, I'm going to turn it off because I'm going to show the trimmed or appropriate box plot. From here, I can now see that this is an outlier and this is an outlier, and that the end of the normal data should be right here. Now, one of the things that this dynamic graph will let students do is explore what will happen as they change values. So if I change this value, I can see my interquartile range changing, and I can see the boundary of what constitutes an outlier changing. I can actually get to a point where one of them, and just barely, is within the data set, but the other one is not. This allows students to have a dynamic exploration of really understanding when you get to an outlier versus a data point that's within the set. I'm going to go ahead and I'm going to put these back to where they were because I want to show one other aspect of box plots and examining the data using box plots. We're now back at our left skewed graph. Well, how do we really talk about data in terms of consistency or variation? Well, a single box plot is almost useless for that. We want to be able to compare it to another box plot. The box plot that I've just added to the screen is a normally distributed box plot. It has the same endpoints, but the data set is perfectly uniform, or excuse me, not uniform, perfectly normally distributed. This helps me contrast my two box plots and really understand what it means to have greater variability or greater concentration. Right now, the data sets as a whole show the same overall variation from 1 to 7, but they show differences in variation within the quartiles. For example, quartile 2 for the lower graph shows a greater variation in the data than quartile 2 for the upper graph. By the same extension, the highest quartile shows greater concentration or greater consistency in the lower graph than it does in the upper graph. And students can actually now dynamically change things so that we get a graph that's more concentrated or more consistent than the upper graph, or a graph that shows greater variation than the upper graph. This dynamic exploration lets students explore different things and show their understandings in different ways. In addition to all of this, students can actually use things like Google Sheets or Microsoft Excel or any spreadsheet program to further dive into data and see what happens. Most spreadsheet softwares have quartile measurements and quartile functions, as well as mean and median functions and will allow students to dynamically change the numbers and see how the mean or the median will change along the way. I hope that this video provides teachers with some ideas for how they can let students explore what all of these things mean, particularly the differences in centers, before we worry about calculations. Generally speaking, we want the calculations to serve the purpose of the understanding we've established. When students understand the different centers and the different calculations and why they need to do them, they're going to be a lot more willing to persevere through those calculations, and they won't seem arbitrary and capricious. I hope that everybody enjoyed this video. If you have questions or you have video ideas, please feel free to email me, and thank you very much.